second poll. That one comes pretty close to the beginning as well. So hello, everyone, and welcome back to another Qubit by Qubit lab. This is lab number 2, and we'll be talking today about trigonometry and coordinate systems. So again, my name is Corbin. I'll be your TA today, and we'll have some fun learning about these math concepts. Now, I want to address a few just like logistical points, I suppose, before we keep going with this lab. Number one, we heard some feedback from some people that the red pen color was not showing up very well on some screens. So I'm going to try and stick to using just darker colors like blue or black pen for the remainder of the semester. If I switch away from that, just wait for one of the question periods and feel free to remind me to switch back to the darker pen colors. Second, sort of like logistical note, we just wanted to take this opportunity to kind of clarify the discrepancies this week between the lecture content, the homework, and the lab content. So just so that we're all on the same page, the lecture content, as you've probably figured out by now, is somewhat different from what's being asked on the homework, and indeed is different from what's being offered in the lab today. The lab content should be closely related to the homework. And so the intention here is to get you familiar and comfortable with all the topics you need to do the homework. The lecture this week was intended to be sort of a higher level overview of some of the quantum computing concepts that will come up throughout the course. So pretty much everything you heard in this week's lecture will come up again later on in more detail. And when it's properly introduced in more detail at that later time, then we'll have labs and we'll have homework that cover that content. So you can really consider this week's lecture to be sort of an overview or a preview of what's to come. It is certainly all relevant, as is all of the math we're about to see, but it is just sort of a higher level overview of what's going to come soon. So I hope that helps clear up any confusion that you might have had on the content this week. Turning to our lab topic here, talking about trigonometry and coordinate systems, the first thing I like to point out with this topic, and you might recognize this if you went to the trigonometry review earlier on in the program, is that trigonometry, despite sounding a lot like triangles, really for the purposes of quantum mechanics has pretty much nothing to do with triangles. And so it's more helpful to think of it in terms of circles. And so everything we do today is going to be trigonometry based on circles. And even though I know that makes pretty much no sense as far as the naming goes, that is the way it works in quantum computing, and that's how we're going to be introducing it today. Now, a little bit on why this actually matters for quantum computing. I'll just preface this by saying you do not need to know this. This is just a bit of an extra tidbit to give you some idea of why trigonometry is actually relevant to quantum computing. There's a useful sort of diagram you can draw, and you'll see this later on in the course as well, that might give you an idea of where circles come in. So I'm going to start off on my coordinate axis plane here. I'm just going to draw a unit circle, or at least try to draw a unit circle. We'll talk about unit circles again in just a moment. But on this diagram, you can actually pictorially represent the qubit states, ket 0 and ket 1, which you learned about in lecture, are just the quantum equivalents of our classical bits 0 and 1. You can actually draw them in this fashion on the coordinate plane. And every quantum state that is a superposition of 0 and 1 is a point somewhere on this circle. So for example, if I had a superposition that was evenly, 50-50, 0 and 1, it would be sort of 50% toward, or sorry, 50% between the 0 and 1 points on the circle. Now, it turns out that there are a bunch of other points around this circle that are also superpositions of 0 and 1, and we'll talk more about that later in the course. But this is sort of the most fundamental reason why circles are actually relevant to quantum computing, is because quantum states can all be placed on circles or spheres or sometimes even higher dimensional objects. And so this kind of circle math, aka trigonometry, is going to be super relevant for us. So a quick overview for what we'll do today. We're going to do a quick refresher of the ground rules, which is the same slides that we saw last week. So I'll go over them a little bit faster, but just to make sure that they are still fresh in your mind. Then we'll do our pre-lab student feedback. Now, note this will be a little bit different from last week. Last week we did this on Zoom. This week we will be doing it on Canvas. So I'll give you more instructions on how to do that in just a bit. Also a new section this week, we'll talk about popular questions from last week. So this is primarily things that came up a lot on Piazza that we just want to address and make sure that everyone sort of gets the answers that they need. Then we'll do our core lab content, which is the trigonometry stuff and coordinate systems. And finally, we'll have the same post-lab student feedback at the end. So as we talked about last time, some basic ground rules. The biggest thing for Qubit by Qubit is really this top point here, which is that we want to ensure every student participating in the lab feels welcomed and included. So what do we mean by this? We mean that every student should feel welcome to ask questions. We want everyone to feel as though they belong in this group. The reality is that quantum computing is difficult for a lot of people to learn. And so we don't want anyone to feel bad if they're struggling or don't get a handle on concepts. It's also very important to remember that there's a huge range of skills in this program. There's a lot of students who are obviously in high school, but there are also students who have gone through more education and might have more of a background in things. So all that just to say, please try not to feel bad, try not to feel discouraged or embarrassed if you don't feel perfectly up to date on all of the concepts. That's perfectly normal, and we just want to make sure that you feel included. Some ground rules for Zoom. We just ask that you don't spam the chat or Q&A with repeated questions or messages. I think this generally went fine last week, so I'm not too concerned. Don't put answers to problems in the chat or Q&A unless I ask you to. So today we are actually going to have an example of something where I ask you to throw questions actually into a Zoom poll. But anyway, this is just to make sure that everyone has a chance to do the problems before they see the answers. Keep your questions relevant to the topics being discussed. This is, again, we don't have tons of time in these labs. We only have an hour together. So just try to keep your questions nice and focused. And only raise your hand if the TA asks you to. As I said before, I don't really plan on using the hand raising feature. So I would say just forget about it for now. As instructors and TAs, we want to hear from diverse voices. So remember, we had this motto, step up, step back. Step back, referring to people who normally find themselves very willing and open to share questions or misunderstandings and sort of speak up about their own confusion. We would ask them to step back and leave room for the second type of student, who are those who are typically more shy, maybe not as willing to ask so many questions. And to those students, we would say, please step up, let your voices be heard. As we said on the previous slide, we want to hear from everyone. We want to have a genuine feel for how every student is doing in the course. And finally, we will not be able to address all content questions in lecture or lab. So if you are curious, if you want to learn more, feel free to follow along on Piazza. I know there have been lots of interesting questions on there this week. If your question on Piazza relates directly to the content, be sure to throw it into a folder such as week 1 or week 2, just so that we can answer it appropriately. So that should all be a review, but hopefully it's helpful to keep these things fresh in your mind. So we're going to move on to the pre-lab Canvas feedback. Now, as I said before, for the first time, this is going to be happening on Canvas. So go ahead and get your browsers opened up and go on to Canvas. On there, you should see a quiz that indicates the lab number. And our lab number today is 2A. So make sure you select the right lab number. And then the quiz should also have a password. And the password for today's lab pre-feedback quiz is 4445. So I'm going to leave this slide up, and I'm also going to ask if we can have the chat opened up, just in case people have any issues with Canvas as we're going through this. And I am going to give a little bit more time to do this week. Just it's the first time doing it, so if you have any problems that come up with Canvas or submitting this quiz, feel free to pop them in the chat, and we'll see if we can sort them out for you nice and quickly. If not, we'll refer you to something else. So with that said, lab number 2A, quiz password 4445. Go on to Canvas and let us know how you found this week's content. I'm going to give us just a couple of minutes here to do that, and then I will check in when you're done. Okay, so one person says the code won't work for me. I'm assuming that's the password. So just make sure that you are in the correct lab number quiz. So there are different quizzes for different lab sections. Just make sure that you're in the 2A lab section. And then the quiz password 4445 should work. Where in Canvas is this survey? And actually related, can you show us how to sign on to Canvas? I don't have access to Canvas as a student, so unfortunately I can't show you exactly what this should look like, but it is posted as a quiz on Canvas, so there should be something along those lines to lead you to the pre-lab Canvas feedback. Okay, so to anybody who is having issues not seeing lab 2A, for example, so one person said they only see 2B. So for those people, our Q by Q Zoom just sent a message in the chat that says, if you don't have a Canvas account yet, please use Airtable form for attendance this week. If you are in the wrong lab section, so you're seeing 2B, but you should be in 2A, please fill out that same form. Our administration team will follow up with you afterward to get anything like that sorted out. Awesome. Okay, so Jmail just posted a more detailed description than I am able to give on how to get to the 2A quiz. How can we make sure we submitted the quiz properly? I believe, I mean, if you hit submit on the quiz, you should just select, there's only one question. So it'll just ask on a scale of 1 to 5, how would you rate this week's content? You answer 1 to 5, click submit, and then it should be submitted just fine after that. The difference between lab 2A and 2B, I believe that 2B is going on at the same time, correct? But you have to be added specifically to the Zoom session as well as the Canvas quiz. So if there's a mismatch between those two things, you can go ahead and fill out the Airtable form that our moderator put in the chat earlier. If it says the quiz is locked, just make sure that you plug in the quiz password correctly. That should allow you to access it. So once again, as we are wrapping up here, I'm hoping that most people were able to submit successfully, but if you were not, make sure that you fill out you go to the Airtable link that our moderator sent in chat and fill out that form just to describe the problem that you're having. It will also log your attendance for this week. So no worries if you can't fill out the Canvas quiz, just fill out the troubleshooting form instead, and your attendance will be recorded. Okay, so before we move on, just to summarize, I guess, you either should have submitted the quiz on Canvas, gone to lab number 2A, typed in the quiz password, filled in the quiz, clicked submit, and if it says score 1 out of 1, as Luna just sent in the chat, that means it's okay, yes. So if you see that, you've submitted the quiz, you see your grade as 1 out of 1, you should be good to go. If any step in that process did not work for you, go to the link that was sent by Q Zoom in the Zoom chat, go to that Airtable link and fill out the form. Your attendance will be recorded, and then we will also follow up with you with any logistical challenges. Okay, so I am going to go ahead and move on. So hopefully, I'm hoping that worked for most of you, but again, we'll get any difficulties figured out as we move on with the course. Okay, so questions from the past week. Now, the first one that seemed to trip up a lot of people was combinations of logic expressions. So there was a question on the homework that looked something similar to this. I don't know if it was exactly the same, but I'm just going to show how I would work through a problem like this. And hopefully that helps with any related homework questions. So the first thing to notice with this is that unlike some of the things we saw in the previous slides, there's actually 3 input variables here, A, B, and C. So when we go ahead and make our truth table, we have to remember to include all 3, A, B, and C, all of our inputs. So remember the truth table is just your inputs and your outputs. So we have 3 inputs here. Now I'm just going to go ahead and fill in every possible combination of these 3 binary bits. And if you notice, what I'm actually doing here is I'm counting up in binary. Now, no worries if you can't immediately see that. It works to just sort of fill this out in any order you like, as long as you hit every combination of 0s and 1s exactly once. So now that I've got my truth table set up, the way to tackle these problems is very similar to how you would tackle a regular algebra problem. So for example, if I had something that was like 4 plus 2 times 6, for example, what I would do to solve this problem in sort of like normal algebra, you always start inside the brackets. You would figure out what's inside the brackets first, and then you would figure out what the entire expression evaluates to. So for a logic gate, we're going to do the same thing. We're going to figure out what's inside the brackets here first. That's going to be A NAND B. I'm going to go ahead and switch colors here. And what I like to do for these kinds of problems is I like to create a column in my truth table for every bracketed expression. So we have A NAND B in brackets here. A NAND B. I'm going to create a column in our truth table for A NAND B. And then just for convenience, I'm going to pull up the truth table for our NAND gate. So over here, we have the truth table for NAND. Over here, we have the truth table for XOR, which we're going to need in just a moment. But for now, we're going to focus on NAND. And notice that our expression is A NAND B. It has nothing to do with C. So just for clarity, I'm going to scratch out C because we don't actually care about that column for this computation. Now, I'm just going to go and fill out this A NAND B column according to the NAND truth table. So let's look at our first row. We have A and B are both 0. So the corresponding row in our NAND truth table, A and B are 0, means that A NAND B is going to be 1. The next row happens to be the same. It's 0 and 0. So A NAND B is the same thing. It's just 1. And you continue in this fashion, just sort of checking, okay, so if A is 0, B is 1, I go to the second row in my NAND table and I see that the result is still 1. And you'll notice that these ones are also 1. Only in the final row, when we have A equals 1 and B equals 1, do we get zeros. So hopefully you can see here how essentially I've just almost like expanded this truth table out into this column. Okay, so now that we have this figured out, let's move on one more step and look at the entire expression. So I'll go ahead and switch colors again here. And then we'll make a column for our final expression here, which is the whole thing, A NAND B, XOR C. And this is sort of the final answer that we're going for. Now for this, notice that my two input variables here are A NAND B and C. So I will care about this column, A NAND B. I will care about this column, C. And for this, I actually don't care about the first two columns because they don't show up here. Only A NAND B, that whole bracketed expression, shows up. So if we go ahead and do the same thing now, we're looking at A NAND B XOR C. So I'm going to take first A NAND B, which is a 1, XOR C, which is a 0, and find that row in my truth table. So that's the 1, 0 row. Go over here to my XOR truth table. I have 1, 0, gives me a 1. I'm going to do that one more time just to make sure that it's clear how that worked. We have A NAND B, all in brackets, is our first input. So our A NAND B here is 1. XOR C is the second input, C is 1. So if we have 1, 1 row in our XOR table, that actually gives us 0. And I would just keep on doing this. I would always line up our A NAND B column into the first column of the truth table, our C variable into the second column of the truth table, and then look up what the output should be. And if you do this for this example, you should get something that looks like this, if I've done that correctly. So I hope that clears things up a little bit. Just to kind of summarize how I did that. First step was to draw the truth table with all of our inputs. So remember, we had A, B, and C as inputs. And so we had to draw our truth table with 3 input columns. The second step was to write columns for bracketed expressions. And then the third step was to write a final column for the output. And then that's how you would get a truth table for something like this. Okay, second question from last week was more of a general one. So I'm actually not going to work through any example problems or anything here, but it's just a general question. How exactly are these logic gates? So remember, logic gates just refers to things like and, not, or, etc. All those things we talked about last week. The question was, how are they actually made? What's inside of them? So they're made from these things called transistors. And I actually alluded to this a little bit last week when I said that computers, instead of having sort of 10 fingers to count like humans do, computers have these little switches. And the switches can be on or off. The way that's actually made in real life is by having a little unit called a transistor, and we either allow electricity to flow through it, so the current is on, or we don't. And that sort of represents this on or off switch. Now, gates are used by just combining these switches in clever ways. We won't go into exactly how that's done, but basically at the core of all of these logic gates is these transistors. And then as you sort of saw in the homework, you can use these basic logic gates to come up with more complicated circuits that have, let's say, 3 inputs, right? And a truth table that's 8 rows long. And you can imagine building larger and larger circuits by combining more and more logic gates. And if you keep combining these things all the way up, if you get hundreds and thousands and hundreds of thousands of transistors and logic gates all put together, finally you get up to the level of, for example, a Zoom call or something. But there are many, many layers of abstractions in between those things. However, at the sort of base level, it is still just these transistors and logic gates that makes everything on a computer happen. Okay, so that was all the content we wanted to cover from last week. So now let's go into the learning objectives for this week. First up, we are going to have a little bit of a review of trigonometric functions at various angles. So this is essentially finding the values of sine, cosine, and tan for special angles. Next up, we are going to solidify our understanding of coordinate systems. So we're going to go over what Cartesian coordinates are, what polar coordinates are, and how you convert between them. And then if we have time, there's some purely optional content at the end to go over summation notation. So let's start off with trigonometry. And as I said right at the top, trigonometry has not a whole lot to do with triangles. It's really about circles, or at least that's how we want to think about it for quantum computing. So we're going to start off with the definition of something called a unit circle, which is a pretty appropriate name, I would say. It is clearly a circle, and it has radius 1. So that's what the unit part of the definition means. It just means that it has radius 1. And so when we say it has radius 1, we mean that if we go from the center of the circle to any point on the circle, so for example, here I'll just go straight across the x-axis, and we get to a point on the perimeter of the circle, we know that that distance is going to be exactly 1. So here our point is at x coordinate 1, y coordinate 0. Likewise, if we went straight up along the y-axis, again, we've traveled distance 1 because the circle has a radius of 1. And so we get an x coordinate 0, y coordinate 1. Now, the same thing goes even if you had a point sort of somewhere out here on the circle. If we drew the radius out to that point, this would still have a radius of 1. And so this is sort of the defining characteristic of the unit circle. Now, we can break this down into its components, and we can look at sort of the A and B being the x and y coordinates of our point on the side of the circle here. And I'm going to remind you of the definition of a circle, which is an equation that says x squared plus y squared equals r squared. And all this is telling us is any sort of xy point that appears on a circle will satisfy this equation. So if we try plugging in our magical AB point over here into this formula, the x coordinate is A, so we square that. The y coordinate is B, square that. And the radius, remember, we're in the unit circle, so the radius is always 1. 1 squared is just 1. And so we get that A squared plus B squared will always be 1 for a point on the unit circle. So if we want to define our sine, cos, and tan functions based on this, how do we do that? Well, you might have learned something that was like SOHCAHTOA. That's how I learned it. Which, if you've never heard of this, that's totally fine. The whole point of what I'm about to say is that you don't need this for quantum computing. You may have learned some kind of memory trick like this to remember the definitions of these functions. What we'll say right now is this is actually not the thing we want you to remember. Instead, the thing that we want you to remember is a point on the unit circle has coordinates cos theta, sine theta. So the x coordinate is cos theta, the y coordinate is sine theta. How exactly we get that, you don't have to worry about. You just have to remember that we essentially say, by definition, this is how we're going to define cos theta and sine theta. Now, the final one is tan. And for this one, we're again just going to have a definition that tan theta will always be equal to sine theta over cos theta. That's something you just kind of have to memorize, I guess. But the main point here is that whenever you know the coordinates of a point on a circle, you know cos theta, sine theta. And so you can just plug it into this formula for tan, and you'll always be able to find tan theta as well. So if we go ahead and look at our point that we had from before, we said that the x coordinate of this point was A, the y coordinate of this point was B. And from what we just said, because this point lies on the unit circle, its coordinates are exactly, by definition, cos theta, sine theta. So this actually allows us to define what sine, cos, and tan are. First of all, if we just compare the y coordinates of our point, notice that our b value here has to be exactly equal to sine theta, because both of those are the y coordinate of the same point. And so we end up with sine theta equals b. Same argument for the x coordinate gives us that cos theta must equal a. And then, as I said before, as soon as you know sine and cos, you automatically know tan by just plugging in those numbers. So if you see how we got this, tan theta we said by definition was just sine theta over cos theta. And then we just went ahead and plugged in these numbers to get tan. So let's do a quick practice problem using what we've just learned. So we are shown a picture of the unit circle, and we see that there's a point on this unit circle with coordinates √3/2, 1/2. We're told that the angle down here is pi/6, and we're told to find sine, cos, and tan of pi/6. So just like I said before, the first thing to start off with is our definitions of sine and cos. And for this course, the way we define sine and cos is as the coordinates of a point on the unit circle. This point is indeed on the unit circle, as you can tell. And so its coordinates, are given by cos theta, sine theta. Now, what exactly is theta in this case? Well, theta has already been given to us, although they didn't use its name. They just told us that this angle was pi/6. So I'm going to go ahead and replace our value of theta here with pi/6. Now, how do we actually find sine, cos, and tan? Well, we do the same trick that we had in the previous slide, which is to say that the y coordinates, sine pi/6 and 1/2, must be the same because it's talking about the same point. So sine of pi/6, the y coordinate, has to be equal to the y coordinate we're given, which is 1/2. Same argument for cos pi/6. The x coordinates must be the same. So all I'm doing to get this is I'm remembering our definitions of sine and cos. They are just the x and y coordinates of a point on the unit circle. And then because these coordinates here are talking about the same point as these coordinates here, we know that the x coordinate and the y coordinate must be equal. Next up, we need tan. So let's look at tan pi/6. Now, by definition, we remember that tan was sine theta over cos theta. And luckily for us, we already figured both of those out. Our sine was 1/2, and our cosine was √3/2. Flip these around, so it's 1/2 multiplied by the reciprocal of the denominator, and we get 1/√3 as our value for tan. So we'll go on to the next slide just to double check our answers. And indeed, we have sine is 1/2, cos is √3/2, and tan is 1/√3. Let's do one more example. So here we have a point that is, not in this first quadrant of the circle. It's all the way over here. But actually, the point of going through this example is that nothing really changes. We begin the same way with our definition of sine and cos, which does not change. The sine and cos of an angle are always given by the x and y coordinates of a point on the unit circle. In this case, we're shown that the angle here with the x-axis is 4 pi/3. So I'm going to go ahead and substitute that in for theta. And now, just like before, we know that these coordinates here describe the same point as these coordinates here. So their x and y components must be the same. Looking at the y coordinate, we have that sine of 4 pi over 3 is equal to minus root 3 over 2, just looking at the y coordinate of the point we were given. And likewise, cos of 4 pi over 3 is equal to minus 1/2. So the only trick here is remembering the definition of sine and cos is the x and y coordinates of a point on the unit circle. Next up, to figure out tan, it's the same trick again. So tan of 4 pi over 3 is going to be sine 4 pi over 3 divided by cos 4 pi over 3. We already figured out both of those things here. So we'll just go ahead and plug those in. Our sine is minus root 3 over 2. Our cosine is minus 1/2. The negative signs cancel out, and then we'll do the same trick multiplied by the reciprocal. And this time our tangent is square root of 3. Again, I'll go to the next slide just to check our answers. So sine minus root 3 over 2, cos is minus 1/2, tan is root 3, as expected. Okay, so I will pause again here for any questions so we can go ahead and open up the chat again. If you have any questions about the content I've covered so far, please feel free to throw them in the chat, and I will do my best to answer them right now. Okay, why is this relevant to quantum computing? Good question. Okay, yeah, so why don't I talk briefly about the analogy I made to quantum computing just at the beginning of the lab. Well, what I can draw a unit circle, and we can actually represent any quantum superposition as a point on the unit circle. Now, again, the details of this will be introduced in future lectures, but essentially, instead of the x-axis, we think of this as the ket 0 axis. And instead of the y-axis, we think of this as the ket 1 axis. Now, if you had a point that was sitting right here, that would be the state ket 0. This would be the state ket 1. But if you had a point anywhere else on the unit circle, that would be some superposition of 0 and 1. And how exactly you describe those points is defined by trigonometry. So because all quantum superpositions have sort of this very close relationship to a unit circle, the math involved with quantum computing tends to heavily rely on trig functions. Okay, so you were also asked, does it matter if you rationalize the answers or not? No, so if you had something like, we had as an example before 1 over root 3, you could rationalize this if you wanted to. And so the way you would rationalize the denominator here is you would multiply it by root 3 over root 3, which we can tell is just 1. And you would end up with root 3 over 3. You are totally fine to do it this way, but you won't be deducted any marks for trying to plug it in as just 1 over root 3. That's totally fine. Does the cos and sine correspond to x, y for the non-unit circle? So we're going to talk about the non-unit circle in just a moment. So just hold on for that. Next up, isn't ket 1 supposed to be on the top and ket 0 at the bottom rather than the middle? Okay, so there is a distinction between what I've drawn here and what's called the block sphere. These are two different things. So I think possibly what this is being confused with is the block sphere. Don't worry if you don't understand what that is right now. It certainly hasn't been introduced yet. You will learn about the block sphere very soon though. And in that context, it will look a little bit different. But we'll go over that in a lot more detail. On the homework, should answers be rationalized? I don't think it matters. If you wanted to be really safe, you could go ahead and ask on Discord, but I think you'll just be typing in the answers as numbers anyway. And so, Okay, so I think we'll shut off the chat here and I'll just answer the last couple of questions that came in. There's a unit circle on homework 2. So do we have to memorize the values or will we have to be getting the circle every time? I don't think that you certainly don't have to memorize the whole circle that's given on the homework. I believe that every time you're asked to compute these trig values, you'll be given a diagram like that. So as long as you know how to read the unit circle, you should be good to go. The Z gate and the H gate, the other points of the unit circle. Yeah, exactly. So I won't go into a lot of detail on that right now, just because we will learn about it in more depth in future lectures. But you're absolutely correct that the H gate and the Z gate and stuff, they correspond to certain movements around this circle. And so oftentimes it's very helpful to visualize things as a circle. Alrighty, so let's go ahead and move on to our second big topic, which is coordinate systems. Now, I'll do just a brief introduction, I guess, of the motivation for coordinate systems. One quick note, though, is just within the context of quantum computing, you might hear coordinate systems referred to by a different name. And I guess this is a slightly separate topic. It comes up in linear algebra a lot. But coordinate systems are basically the same thing as these things called bases. So we will start talking about bases later on in the course. Don't worry too much about this for now. I'm just kind of giving you a heads up that coordinate systems and bases are, generally speaking, very related. And so as we talk about coordinate systems here, really what we're prepping for is a discussion of bases later on in the course. So let's just ask a very simple question to start off with here. What exactly is a coordinate system? If I give you a point somewhere out in the middle of nowhere, the basic responsibility of a coordinate system is to somehow give me a way of conveying to you where this point is. So one way I might describe this is I might tell you that this point is sort of, it's about, I don't know, 15 centimeters from the left side of my screen. And it's about, I don't know, 8 centimeters from the top of my screen. And given just that information, these two numbers, 15 and 8, you would be able to tell exactly where this point is. And so that's the job of a coordinate system. The job of a coordinate system is to give you a way of describing where points are in space. So I'll draw a little bit of a more traditional diagram here. This is what you're probably more used to seeing. I just think that, we see graph paper so often in math, sometimes you lose the basic motivation for why we need these things. But yeah, all that a graph is trying to tell you is where a point is. So again, here, by telling you that this point is at 4,3, or actually, I think I have that on the next slide. But basically, yeah, telling you that this point is at 4,3 is all the information you need to know to figure out where it is. There we go. Now, my question to you to think about is, why do we necessarily have to have these axes aligned as we do? Why do we have to have one that's horizontal and one that's vertical? Why couldn't we have a coordinate system that, for example, looked something like this? Now, I know for what we've done here, we've just obviously tilted the picture on its side, but I hope you can see that we can still describe where this point is using this new kind of weird axis system. So in this case, the point would be labeled by 5, 0. Why is that? Well, I still go 5 units up the first axis and 0 units on the other axis. So the point is at 5, 0. And this describes the exact same location in space as the previous 4, 3 did. It's just in a different coordinate system. Here we've rotated our whole graph to use a different coordinate system. Now, on the topic of different coordinate systems, let's go back to our basic one here that we're all familiar with. We've seen in each of the past slides that you generally need 2 numbers to describe where a point is, right? So on our first slide, we had the point being at 4, 3. Then we rotated our grid and we saw that it was instead 5 units along this new rotated axis and 0 units along the other axis. Is there any other way we can use two numbers to describe where a point is? And this is where polar coordinates come in. So the first number I'm going to use is just the distance from the origin to the point itself. And so this, even if if the point was up here, no worries, the distance still just goes straight up to the point itself. And I'm going to label how long that is. So for example, here the distance is 5 units. We know from when we rotated it, if you just go straight from the origin to that point, it's 5 units away. Oops. Now, the second sort of number I'm going to use here is the angle. Now, why do we need the angle? If you think about just me telling you that a point is 5 units away from the origin of our coordinate system, that could be a point down here as well, because this point is also 5 units away from the origin. Likewise, it could be a point up here that's also 5 units away. Could be a point up here that's also 5 units away. And so what we actually get is there's sort of a circle that forms of all possible points that are 5 units away from the origin. So how do I tell you exactly where this point is? I define an angle. We'll call this theta. It's about 0.2 pi in this case. Now, if I tell you what this angle is, I cannot be at any of those other points I drew because they're all going to be different angles away from the x-axis. So in fact, by specifying the distance away from the origin and the angle from the x-axis, we can uniquely specify the position of a point, just like we can with our regular Cartesian coordinates. So let's talk about how to work between these two systems. So we're all very familiar with our XY Cartesian coordinate system. Sometimes you'll also hear this called the rectangular coordinate system. Now, the one that we've just introduced is called polar coordinates. And to use that, we use r as sort of the distance away from the origin. It's supposed to be reminiscent of radius. And theta is the angle away from the x-axis. So again, we're just using our two numbers here to describe where a point is in space. Now I'm going to go ahead and draw my own little coordinate system down here. And I'll just give ourselves a point up here. And let's talk about how to go from Cartesian to polar coordinates. So let's say that I know this point has Cartesian coordinates a comma b. So what does that mean? That means that the x coordinate here is a. Oops, sorry, I'll draw that a little further down. This is a. And the y coordinate here is b. Now, somehow from these two numbers, I want to get the radius r and the angle theta. So I'm going to go ahead and draw these two things on the diagram as well. Remember, the radius is just defined as a straight line out from the origin going up to our point. I'll just label that as r. And then the angle is the angle away from the x-axis. We'll call that theta. Now, let's first try and figure out how we do r. Now, you might recall from high school math something called the Pythagorean theorem. Pythagorean theorem. And it applies to right triangles. So we just happen to have drawn a right triangle here. If I just add in a little right angle there. And so we can use the Pythagorean theorem to solve for r. We'll take the squares of our two side lengths, a squared plus b squared. And we know that that's going to be equal to the hypotenuse squared, which in this case is just r squared. We want to solve for r, so we'll take the square root of both sides, and we get that r is equal to the square root of a squared plus b squared. Cool, so we've solved for r. The only little bit of a problem with this is that normally when we take the square root of a number like this, we would label our solution as either plus or minus that value. Luckily, we don't have to do that here. And the reason is just that the way we define this r value, this radius, it's always going to be just a distance away from the origin. So we can always just take the value to be positive, and that's not going to be any issue. All right, next up, how do we find theta? Well, for theta, we are going to use a little bit of trigonometry, some of the stuff we just learned. And the first thing that I will note here is the definition of a unit circle. Now, I know that we aren't exactly on a unit circle here, but I'm going to draw sort of the same diagram. So we have some kind of circle going around here like this. And it turns out, as I will describe in just a moment, that the x and y coordinates on a non-unit circle are just going to be multiplied by r. So what that looks like is the x coordinate becomes r cos theta, and the y coordinate becomes r sine theta. I'll explain this a little bit more on the next slide, but for now, let's just remember that this is the xy coordinates you get for a non-unit circle. Now, we have theta appearing here. In order to get rid of these r's, we would like to be able to divide one of these values by the other. That way the r's would cancel out. And it turns out that tan theta gives us the perfect way to do that. Remember that tan theta is defined as sine theta over cos theta. And if we plug in our values here for sine theta and cos theta, we actually have that the r's will cancel out. So remember, we had that, actually I'll write this just over to the side. If we write our b divided by a, we can just compare the y coordinates here and compare the x coordinates here. So our b is equal to r sine theta. Our a is equal to the x coordinate, which is just r cos theta. The r's will go and cancel out. Sine theta over cos theta, we remember, is equal to tan theta. And so this is the key result that we need to solve for theta, because now we can take the inverse tan of both sides, and we get that theta is equal to the inverse tan b over a. Now, that was quite a bit to follow, so I'm just going to go ahead and throw a summary up here. I guess I'll have to erase a little bit. So as we said, our r value, the radius, was equal to x squared plus y squared by Pythagoras. Gives us that. And then the next value we had was our theta equals tan inverse of y over x. So again, I was using b and a. It's the same idea here. We have y over x to give us the value of theta. So at the end of the day, it's certainly nice to know how you derive all of these things. But for the purposes of the homework assignment, I would say all you really need to know is these two formulas. Because on the homework, you're going to be asked to convert from Cartesian to polar coordinates. As much as sort of these derivations might have seemed complicated, the reality is that converting between coordinate systems is actually really easy. You just have to plug in numbers into these formulas. So for the homework, that's all you do. You get your x and y, you plug it into this formula, you plug it into this formula. You are allowed to use your calculator for this particular question on the homework. And so you just plug these things in, hit enter, and you'll get your values for r and theta. Let's go look at what the other direction looks like, converting from polar to Cartesian. Luckily, I think this one is quite a bit more straightforward. So I'm going to start off with my same set of axes here. I'll draw ourselves some point. But now, instead of being given the xy coordinates, we are given the r theta coordinates. So what we know is that this point is a distance r away from the origin, and it makes an angle theta with the x-axis. Now what we want to find is we want to find the x coordinate of this point and the y coordinate of this point. So like I said before, we can sort of imagine this point lying on a circle, just like this. And the only difference here is that our circle is radius r instead of radius 1, like the unit circle. As I said before, the only difference there is that our coordinates are going to be given by r cos theta and r sine theta. And in fact, this pretty much gives us our answer, because when we write our coordinates in this way, we have written them in the Cartesian coordinate system. So this is the same as saying x comma y. And so if we wanted to solve for x, we just noticed that these two coordinates must be the same. So x equals r cos theta, and then likewise, y is going to be equal to r sine theta. I'll go ahead and throw that up on the slide. As before, it's okay if you don't really see how this works at first. I think that you will get it in time, but at least for this week's homework, all you really need is these two formulas. X equals r cos theta, y equals r sine theta. Again, you're going to have a calculator. So when you're given r and theta, you just plug them in to these two equations, and then you get your x and y values. So let's go ahead and do a quick example, converting from polar to Cartesian coordinates. So we're told that we have a point at 1 comma pi over 3. Now, if you ever feel confused, when your coordinates have pi in them, it's a pretty good indicator that this is our r and theta. So our r, remember, is just the distance from the origin. Our theta down here is pi over 3. And we are asked to convert to the Cartesian coordinate system. I copied the two equations that we need right here. And so I'm just going to go ahead and plug this in. So x equals r sine theta, it's going to be, or sorry, r cos theta. That's going to be 1 times cos pi over 3. Now you can go ahead and use a calculator to work this out, and you will get that this is equal to half. Again, you will have a calculator for all questions of this nature on the homework. And then for the second one, we have r times sine theta, which is sine pi over 3. And if you go ahead and work this out on your calculator, you're going to get √3 over 2. And that's it. So we literally just have to memorize these formulas, plug in our numbers, and we're good to go. If we have a point that is in a different quadrant of our coordinate system, no worries, it's the exact same thing. So again, these are our r comma theta coordinates. Our radius is just the distance from the origin to our point. That's going to be 1. Theta in this case, remember, is always the distance, or sorry, the angle I should have said, from the x-axis. So this right here is 2 pi over 3. And we're asked to find what the x and y coordinates are. So I'll go ahead and plug in our numbers. We have 1 times the cosine 2 pi over 3. And for y, we have 1 times the sine of 2 pi over 3. Go ahead and plug this into your calculator, and you will get -1 over 2 and √3 over 2. And I'll actually just pause here to say that one of the reasons I like to draw these diagrams for these coordinate conversion questions is that it's a good sanity check. Now, what do I mean by this? If you had gone and plugged all this stuff into your calculator and your x coordinate had been, say you typed stuff in and you got that your x coordinate was half. Let's look at our diagram here. It doesn't really make sense for our x coordinate to be half, because quite clearly it's a negative value of x. So if that happened, just go back, double check your calculations. These things should always work out. So chances are you just made a typo somewhere. This value should turn out to be negative. All right, so I will pause here for any questions from our viewers, so we can turn on the chat again. And if anybody has questions, feel free to send them in the chat. In Cartesian to polar, can we directly take the inverse of sine or cos? Yes, good question. I won't go into how to do that in detail. The basic is just to understand the formula I taught here. But to that question, if you know sort of how to use inverse sine and inverse cos, you're perfectly welcome to do that. What is the equation to go from polar to Cartesian? I'll go back and just leave that up on the slide. These are the polar to Cartesian equations. If we don't have degrees on the angle, we assume it's radians, correct? Yeah, so if you haven't been, or I guess, yeah, the convention used in this course is if I write something with a degree symbol, that means it's in degrees. If I write something with nothing, it's assumed to be in radians. So that's the convention that we use here. Let's see, does the calculator need to be in degrees or radians? It should be in radians. Just go ahead and keep it that way for the duration of the course. And okay, so I think, so all of these questions about the Cartesian to polar equations, etc., you can go ahead and look at the lab slides when they're updated, and they will all be there. Yes, we are working with radians by default, exactly. Okay, and the conversion from Cartesian to polar, the R theorem is weird since the square is being square rooted. Equation A plus B. So if you are confused by those derivations, don't worry too much about it. The equations given in the slides are the correct equations for conversion, so they will work for your homework. Okay, last question I'll answer. Will we ever use any other form of coordinates? Yes, we will use something that's basically an extension of polar coordinates. And so we'll teach that though for sure when we get to it. Okay, so we are at the end of our time here. Now, just like last time, I'm going to spend just a few more minutes going over to cover the optional content. But that content is 100% optional. So if you need to hop off right now, no worries. You can go ahead and hop off the call. There is an important announcement in the chat here. So just make sure that you give that a read. There's a YouTube video there to submit Canvas attendance, the Canvas attendance quiz. And then there's also a form to fill out if you were not able to fill out the quiz at the beginning of the lab. Okay, so next section is completely optional, as I said, so feel free to hop off now if you need to. It's also not particularly long though, so yeah. So we talked about questions. Oh yeah, so I did forget about the post-lab feedback. Unfortunately, a couple people have already left, but I will go ahead and start this poll. This one is going to be a Zoom poll, so don't worry about going back to Canvas for this one. Just go ahead and answer the Zoom poll with how you feel about this week's content. The content here, oh yeah, good question. This should be how you understood the lab content. So all the stuff we went over with trigonometry and coordinate systems, how you feel on a scale of 1 to 5. So go ahead, fill that out. And if you don't want to stay for the optional content, feel free to hop off after that. If you do want to stay, I estimate the optional content will take about another 5 minutes. It's not very long this week. All right, you have a nice day too. Thank you. When do we have to hand in our homework? I believe the deadline is October 31st. Actually, somebody has said it's November 1st. So maybe double check that. I'm not 100% sure. So just double check either on Discord or in the documents that you've been sent. You will be asked to upload your homework on Canvas. All right, thank you everyone. So I'm going to go ahead and end the poll here and move on to the optional content. And we're just going to do a really brief introduction to, yes, I know this is optional, summation notation. Now, summation notation is one of those things that can look really complicated in mathematics, but I promise you it's not a difficult idea. The basic concept is just that we want to make writing long sums of numbers easier. So let's say I had a really long sum, like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. It even takes me a long time to say. And you know, you've done sort of math homework and stuff before. You know that a lot of the time you will sort of carry a certain expression through many lines. So if you were solving some kind of equation, you might have many lines of math that go all the way down your page. And it would be a huge pain to have to copy this thing down every single line on your page. So mathematicians are lazy, so they come up with a good way to sort of summarize this. And the notation just looks like this. So these two equations are exactly the same. They are perfectly equivalent. So this big symbol here is called sigma. So sometimes you might hear people say sigma to represent sum. And it basically just says that you are starting from an I value of 1, going up to an I value of 10, and the whole way along, you're adding up your I values. So if I were to write this out, I won't write out the whole thing, but I would start at 1. I would add my value of I, which in this case is just 1, and I would add it to everything else. So then we get 2 plus 3 plus 4 plus 5, so on, and then it goes all the way up to plus 10. Now you can also do this for symbolic equations like this, for example. So oftentimes you will see sequences of numbers. So if I have sort of a list of 5 numbers, for example, mathematicians will represent it as a variable by just saying a sub k. So a sub 1 would be the first element in the list, a sub 2 would be the second element, and so on. And if you wanted to sum up all of those values, you would write it something like that. Now, that's pretty much all I have to say on summation notations. I will just give one last, I guess, word of advice or wisdom, if you can call it that. And that is to say that as you go through both this course and more advanced math courses, you will see summation notation popping up a lot more. And for a lot of students, this can be scary because it's just a new math symbol. Sometimes you have more complicated things. Sometimes these will all be variables. So you might have like I equals J going up to K of like, you know, A sub I, something like that. And this can just get confusing to look at because there's so many variables and so much going on. So what I like to do in these situations is I will write out sort of the beginning and the end of the sum. So I'll use concrete numbers to make this a little bit easier. So if we had something like this, I would just start writing it out. So I would say, this is going to be, just expand it in my head. We start at I equals 1. So the first value is going to be A1 plus A2 plus, and then we know what happens now. It basically keeps going up all the way. There's some stuff in there. It all gets added on. Plus the final one is going to be A10. So this is still a somewhat short way of writing it. It conveys the same information. But the thing I really like about this form is that it explicitly shows you that all you're doing here is adding. And so really this summation notation, it's not worth it to be frightened of because it's just a way of writing out a sum. So as long as you work and know how to work with sums in mathematics, you will always be fine with summation notation. And so I always recommend to students, just go ahead and expand it to something like this. Hopefully it makes it look a little bit simpler. It also allows you to recognize certain algebraic rules that you can normally use with sums. You can absolutely use with this big sigma summation notation as well. So you're going to see a couple of simple problems related to this on the homework. Basically, you just have to use this definition. So it should be pretty straightforward. But the reason we're introducing it now is that it will come up later. And we just want to start getting you comfortable with the notation. All right, so we can go back to questions in the chat. If you do have any questions about summation notation, that's all I have to say on this topic though. So like I said, it's a really short optional content this week. Kind of like writing loops in coding. Yes, exactly. If you are familiar with how to code, this is exactly like a for loop is the closest thing to it. Do I and K mean the same? Oh, yeah. Yes, good point. Good point. So in these two summation notations, on one of them we use the variable I, on one of them we use the variable K. This is always the variable that increments. So whenever we write one of these summation notation things, the variable that's sort of defined as being equal to something on the bottom is the variable that increments over time, or not over time, but that's the variable that increments with the summation. So yes, in this case, I and K are the same idea, correct? Okay, so I think we will wrap things up here. There was another important announcement by our moderator there. Oh, actually, one more quick question. How do we write something incrementing by 2s? Yeah, good question. So this is definitely optional content. You don't need to know this. But the summation notation as sort of a default does not include a way to do this. You always are stuck with the number just going up one at a time. But if you wanted to say add up all of the multiples of 2, so you want to do like 2 plus 4 plus 6 plus 8, for example, what you would do is you write the summation from I equals 1 to 10, let's say. And then here you would sum up 2i. And so if we just go ahead and expand this out, when our I equals 1, we're going to have 2 times 1 is 2. When our I equals 2, we're going to have 2 times 2 is 4. When our I equals 3, we're going to have 2 times 3 is 6, and so on. And so this is sort of how you achieve that effect with the summation notation. So I hope that helps. I will go ahead and end things off there, but thank you to everyone who stayed for the optional content.